So our next step, this is going to seem like kind of a step back, and it is a little bit. We're going to look at numbers again and some things with numbers to help us get into our next couple of topics. And what we're looking at is we're looking at factors. Factors are numbers that a larger number can be divided by. For example, 24 has many different factors. 24 can be divided by 2, can be divided by 3, can be divided by 4, 6, 8, and 12. All of those are factors of 24. Well, you might be saying, well, it can be divided by 1. Yeah, but anything can be divided by 1, so we don't really consider that to be a factor. Also, you might say it can be divided by 24. The same is true. It can be divided by itself, but every number can be divided by itself, so we don't consider that to be a factor. So any of these numbers, in this case there's 6 of them, are factors of 24. Now if I ask you to factor 24, that's a slightly different request. What I'm asking you to do is take that 24 and break it down into smaller numbers that multiply up to it. The problem is there are several different ways to factor 24. We could have 2 times 12. We could have 3 times 8. We could have 4 times 6. All 3 of those are sets of factors for 24. Or we could do like 2 times 2 times 6. We could have 3. It doesn't have to be just 2 numbers. It could be 3 numbers. Or 2 times 3 times 4. There are a lot of different combinations, basically, is what I'm getting at here. So when we ask you to factor a number, we need to be more specific. Well, before we get into that, I want to look at how can you tell if a number is a factor of a larger number? We have something called divisibility rules. Our divisibility rules give us a little hint to quickly tell if a number can be divided by another number. To tell if a number can be divided by 2, what's the rule? What do you do?
Oh, even.
Yeah, if it's an even number. What does it mean to be even? Well, if the last digit is 0, 2, 4, 6, or 8, that means the number's even. That one's simple enough, right? To tell if something's divisible by 3 is a little more complex. To do that, we look at the sum of the digits. To explain what that means, let's do an example. 741. If I want to know if that's divisible by 3, I'm going to add together the digits. What is 7 plus 4? 11 plus 1 is 12. Is 12 divisible by 3? Yes, it is. So 741 is divisible by 3. Now, divisible by 4, it doesn't really matter because we can divide by 2 twice and you're same as dividing by a 4, right? There is a special rule for 4, but it's one of those that's complicated enough that it's not worth knowing. You just divide by 2 twice. How do you know if something's divisible by 5? The last digit is 0 or 5. Very good. Now for 6, well, again, you can just divide by 2s and 3s. In fact, that's the divisibility rule for 6. If it's divisible by both 2 and 3, it's divisible by 6. 7. There is no rule for 7. 7 is one number that you just have to try. If it can't divide by anything else, just try to divide by 7 and see if it comes out.
That's the worst one for me.
7s?
Yeah, I don't know why.
8. Well, again, there's a rule for 8. but it's not terribly useful. It's complicated enough that it's tough to use. But if you're going to divide something by 8, you can just divide by 2 3 times. So you don't really need the 8. 9, you could just divide by 3 a couple times. In fact, the rule for 9 is the same as the rule for 3. Sum of the digits again, only instead of being divisible by 3, it has to be divisible by 9. For example, 73,413. If we add up those digits, 7 plus 3 is 10 plus 4, 14 plus 1 plus 3 is 18. Is 18 divisible by 9? Yes, so 73,413 is divisible by 9. And 10, of course, last digit is 0. As we go up, we need to distinguish between two types of numbers here. Prime and composite. The word composite means made up of other things. You hear about a composite material. That means it's made up of other materials. Like you might have a plastic metal composite. It's a composite of metal and plastic put together. Or a ceramic metal, ceramet they call it, a ceramic and metal composite, where it's a composite of ceramic materials and metals put together. Made up of other smaller things, basically. So a composite number would be like 8, because 8 can be made up of 2 times 4. There are numbers that divide into 8. It's composite. Prime means it cannot be made up of smaller numbers. In other words, only divisible by itself and 1. So 17, prime or composite? Is there anything that divides into 17? No, it's prime. 21, prime or composite? Composite. It's divisible by 3 and 7. 42, prime or composite? Composite. 51. It's divisible by 3 and 17. Very good. It's composite. So the composite numbers, since they're divisible by smaller things, we don't really need divisibility rules. Like 12. If you divide by 2s and 3s, you can divide by, you don't need to worry about dividing by 12. You just divide out the 2s and 3s. But like 11 and 13, those are prime. It would be nice to have rules for them. Well, there are rules for them. The problem is, the bigger the numbers get, the more complex the rule is. I'll show you the rule for 11. Don't write it down because I'll never ask you to do it. The rule for 11 is so complex that it's easier, especially with calculators, just to take your calculator and punch in, divide it by 11, and see if it comes out with a decimal, or if it comes out with a whole number. To tell if something's divisible by 11. Let's do this. 89,326,543. Start out with the first digit and you take every other digit and you add them up. 8 plus 3 is 11 plus 6. 17 plus 4 is 21. You take the remaining digits and add them up. 9 plus 2 is 11 plus 5 is 16 plus 3 is 19. Now, if you add those up, you get those two numbers. If you subtract them, the difference, in this case, is 2. If that difference is either 0 or a number divisible by 11, like 11, 22, 33, then the whole number is divisible by 11. So this number is not divisible by 11.
That's a lot of work to do that.
It is. It's almost easier just to punch it in the calculator.
Yeah.
This number, however, would be divisible by 11. Because if you did that, you get a difference of 0. This rule? Of course. I'm a math teacher. What else do I have to do with my time?
We know that 89,300,000
26,545?
is divisible by 11.
Of course, don't you?
You just love numbers.
Like I said, I'm a math teacher. What else do I have to do with my time other than sit at home and count stuff?
Is that what you do? You just play with numbers at home?
You used to? So, anyway, so now that we can tell if these numbers are divisible by other numbers, let's go back to the factoring thing again. If I ask you to factor 36, well, there are several factor pairs we could do. 2 and 18, 3 and 12, 4 and 9, 6 and 6. So I need to be more specific. So what we're going to do is we're going to talk about something called prime factor. What prime factoring means is break it up into as many small pieces as you need to until all of those pieces are prime, until none of those pieces can be broken down into anything smaller. To do that, we're going to use a factor tree. So we factor 36. What's one number that divides into 36? Any number. 6. 36 divided by 6 will leave us with 6. So what I've done here is on this row of the tree, 6 times 6 equals 36. So I've broken the 36 down into 6 times 6. Can this 6 be broken down any further? Yeah, into 2 times 3, right? Makes 6. Now the 2 is prime and the 3 is prime, so I'm going to circle them to signify that we're done. Well, over here, this 6 probably can be broken down the exact same way into 2 times 3. Now, everything we have here is prime. What's that? Okay. That's okay. It can be a little crooked. Not all of the branches have to be straight. Nothing. That's why it's prime. Nothing. That's why they're prime. No, remember, dividing by 1 doesn't matter, though. You can divide anything by 1. So the prime factoring of 36, well, you got to be careful. You can't just do 2 and 3. It's actually 2 times 2 times 3 times 3. You got to list them all up because those prime factors have to multiply back up to give you 36.
Serious?
2 times, yep. So 2 times 2 is 4, times 3 is 12, times 3 is 36.
My head.
Stay with us. It's not that bad. So if I ask you to prime factor 42. Okay. If we look at 42, what's one number that can divide into 42? 7. Okay. Or you could have done 2 if you wanted to, because it's even. If I divide 42 by 7, what's left over? 6. 7 times 6 makes 42. Can 7 be broken down any further? No, 7 is prime, so we're going to circle it to signify that we're done. Can 6 be broken down any further? Yes, it can, into 2 times 3. Now those are prime. So 42, the prime factoring is 2 times 3 times 7. Make sense? So I'm going to have you guys try one. It's prime factor 45 for me. Let's take a peek. What's one number that divides into 45? 9 times 5. Good. 5 is prime, so I'm going to circle that. But the 9, 3 times 3. And that is it. 45 is 3 times 3 times 5. Well, why do we care about factoring numbers like this? Well, because factoring is a very powerful tool if we choose to use it in the next topic we're going to cover, which is everybody's favorite part of math, fractions. To understand fractions, recall back to the first day we talked a little bit about all numbers having two parts, a count and a name. And the same with a fraction. It's not two numbers, it's one number with two parts. The 3 is the count. We have 3 of something. Well, what is it? Well, we don't have 3 inches or 3 cows, we have 3/4. The 4 is not a number, it is a name. So what does it mean to be fourths? Well, probably the simplest illustration is to go back to the old elementary school pie or pizza, however you want to think about it. A fourth means that pizza gets cut into 4 equal pieces. So pretend those look equal. So every whole object gets cut into 4 pieces. Or another way to look at it is it takes 4 of these pieces to make one whole object. Now the 3 means that we have 3 out of those 4 pieces. So I know that's kind of a childish illustration, but that's probably the best way to think about it. Now, if we want to rename a fraction, probably the simplest way based on this illustration is to just do this. I'm going to cut it up. I'm going to cut each slice into 3 equal slices. Pretend these look equal also. Well, now, how many pieces does it make to make one whole object? 12, yeah. Each of those pieces, we had 4. Each of them got cut into 3 equal pieces, so 4 times 3 is 12. How many slices do we have? How many pieces do we have? 9. We had 3, and each of them got cut into 3 equal pieces, so 3 times 3 is 9. We now have 9/12 of a pizza. Do we have any more or less over here than we did before? No. 9/12 and 3/4 are exactly the same amount. They just look different. When we multiply the numerator and denominator by the same number, we change the appearance, but not the value of the fraction. Why does it not change the value? Well, because what we just multiplied by was 3 over 3. That's 3 pieces to make a whole object, and we have 3 pieces. In other words, that's equal to 1. You got it. So we just multiplied by 1, and multiplying by 1 does not change the value of anything, but it can change its appearance. So the hard part is looking at something like 2/5 and knowing what we want to change it into. Let's say we want to change that into 30/5. We have to figure out what do we multiply the top and bottom by to do that. What did we have to multiply the 5 by to turn it into 35? 7. So we have to multiply the top, the numerator, by the same thing. 2 times 7 is 14. So 14 35ths and 2/5 are the exact same number. They just look different. So what's this going to be here? 20. Very good. 8 times 4 makes 32, so 5 times 4 makes 20. Very good. We can go the other direction as well. Let's say I have 48. Let's go 60. Let's not 68. Come on. So I have 48 60ths. If I try to visualize 60 pieces to make a whole object, and I have 48 of them, that's kind of tough to do. But we can reduce this to something a little easier to visualize. Just like up above, we multiplied the top and bottom by the same thing. Here, we can divide the top and bottom by the same thing. What can each of those be divided by? Both of them can be divided by 2. 48 divided by 2 is 24. 60 divided by 2 is 30. Now we see that we can still divide each of those by the same thing. It would be, if I do 2 again, or 3, or 6. Let's do 6. 24 divided by 6 is 4. 30 divided by 6 is 5. That's 4/5. Now, many of you are taught that you have to find the largest common divisor, or largest common factor, and divide it out right away. You can see here you don't have to. We did the 2, and once we divided by 2, then it became easier to find other numbers. Once you get smaller numbers, it's easier to figure out what divides into them. We could have divided by 2, and then by another 2, and then by a 3. That'd be just fine. You don't have, or you could have seen right away that both of those were divisible by 12, and it would have been done in one step. It definitely makes it faster to find that largest number, but you don't have to. You'll get there eventually no matter what. We could end up with something like 45 75ths. What can both of those be divided by? Somebody said 5. 45 divided by 5 is 9. 75 divided by 5 is 15. More than 9. Now, both of those can be divided by the same number. 3. Very good. Giving us 3/5. Again, you could have divided by 15 right away, but that's a little bit difficult to see. If you don't see it, just find anything that divides both of them, divide it out, and then go from there. This is also one of the reasons why we did the factoring. What I could have done there, what's that? Well, what we're really doing here is we're looking at factors. 45 is 3 times 3 times 5, if you did the prime factor. 75 is 3 times 5 times 5. How do we know what we can divide both of them by? Well, we can divide both of them by a 3. We can divide both of them by a 5. What are we left with? 3 over 5. That's what reducing a fraction is. It's just canceling out common factors. Dividing the top and bottom by the same number is just that works every time if you can prime factor. Sure. Let's do another example here of 28. Let's do 28. I'll go find something good here. 28 70ths will work. If I prime factor 28, I would get 2 times 2 times 7. If I prime factored 70, I would get 2 times 5 times 7. I just did the factor tree. So if you're looking at 70, 70 is divisible by 10, so it'd be 10 times 7. 7's prime, 10 is 2 times 5. So 2 times 5 times 7. So now I can do, there's a 2 in each of them. I can divide out the 2. There's a 7 in each. I can divide out the 7. I am left with 2 over 5. Now, for many of you, you can just divide them. That's fine. But at some point in the near future, like next week, I'm going to throw in stuff like this. And looking at that, you might be saying, I have no clue. But if we use the factoring approach, this is easy. 12 is 2 times 2 times 3, x to the 5th, y squared. 18 is 2 times 3 times 3, x to the 3rd, y to the 7th. So the 2's cancel out, 3's cancel out. I'm left with a 2 over 3. Cancel out 1x, 2x, and 3x's. I'm left with an x squared on top. Cancel out a y and another y. I'm left to a y to the 5th on bottom. So 2x squared over 3y to the 5th. Now, Riz, that one's a little bit above your head right now. But I want you to see it's the same process, just factor and cancel. Well, we're going to see that again later. And that's why I showed you the factoring with the numbers. Most of you, like I said, can handle just dividing it out. You don't need to do that. But knowing how to do the factoring with the numbers and canceling out then leads us to doing the exact same process once we throw variables in there. That's one of my main goals in this course is to show you all these separate processes with algebra and variables. They are the same processes you would use for whole numbers. You've just never been taught the whole process of doing whole numbers. So anyway, enough of that. Let's look at something like this. When we look at that, the 7, of course, is telling us it takes 7 pieces to make a whole object. If we have 44 pieces, we have more than enough pieces to make a whole object. In fact, we can make several whole objects. How do we figure out how many objects we can make? Divide by 7, okay? So if you take your calculator and do 44 divided by 7, it'll give you 6.2857143 approximately. What's that? Approximately. Now I'm trying to go a few more digits.
What?
I can go a few more decimal places if you
That's
want.
crazy.
I'm not crazy. My mother had me tested. Nothing. Nothing. Anyway, that's a Big Bang Theory. A Big Bang Theory quote. Anyway, what does that tell us?
More than 6.
We know there's 6 whole objects. Very good. But we don't know how many pieces left over. A lot of people will mess up and they'll just take this decimal and say, oh, that's how many pieces left over. We've got to be very careful. The easier way to approach this, I know you don't like doing long division by hand, but you can. 44 divided by 7. 7 goes into 44 6 times. 6 times 7 is 42, which leaves us with 2 left over. 6 and 2 sevens. Not so bad?
Yeah, it was, you know what I was thinking?
Yeah.
When you go to the 6.35, that could just be like 6.3.
Yeah. That's what a lot of people do is they round it up
Yeah.
and just that doesn't work. Let's try 37 over 4. We'll do the same thing. It's 37 divided by 4. 4 goes into 37 9 times. 4 times 9 is 36. Leaves us with 1 left over, so there's 1/4 left over. What do you think? More fun than a barrel of rabid monkeys?
No.
Yeah. Oh, the rabid ones are vicious.
Oh, you said rabbit.
Yeah.
I was thinking rabbit.
Oh, rabbit monkeys?
No, a girl full of rabbits and monkeys.
Oh, gotcha. This, by the way, is what we call an improper fraction.
David on the dollar.
There's nothing improper about it. Nothing, the word improper implies that it's wrong. It's not. There's nothing wrong about it. It's just we don't like it because the numerator is bigger than the denominator, and we could make whole objects out of it. This here is what we call a mixed number. It's mixed because it mixes together fractions and whole numbers. It has a whole number portion. There's 9 whole objects, and there's 1 of those pieces left over that would take 4 pieces to make a whole object, so 1/4. So we can go from an improper fraction into a mixed number. We need to be able to go the other direction. If we have a mixed number, there's sometimes we want to turn it back into an improper fraction. For example, 3 and 5/8. To turn that into an improper fraction, I need to take these 3 whole objects and break them into pieces. Well, how do I know how many pieces to break each of them into? My denominator tells me 8. So 3 whole objects would become how many pieces? Yeah, 3 times 8 is 24. Well, we already had 5 pieces before, so we add the 24 to the 5, which would be 29. So we have 29 eighths. So I'm going to do 7 and 1/3. It's 7 times 3 makes 21, plus the 1 is 22 thirds. Five and 3/4. Yep. 5 times 4 is 20, plus 3 is 23 fourths. What do you think? One more time? Okay. So 8 and 2/5. 8 times 5 is 40. Plus 2, 42 fifths. Going the other way. Yeah, we'll do this, 31 thirds. What's that going to break down into? 31 divided by 3. 3 goes into 3 once. There's nothing left over. Bring down the 1. Does 3 go into 1? Here, 3 doesn't go into 1, but we got to make sure we put a 0 there, right? Yeah, there's 1/3. 10 and 1/3. Very good. I think you got it. How you feeling? We're going to end here, so you got a little bit of time to absorb the fractions. Tomorrow we'll go over any homework questions. We'll review this stuff. On Monday we will start in with operations with fractions. So I want you to understand this whole idea of converting between fractions first. There will be a quiz due tomorrow on Thursday at 11:59 p.m. There's a new homework due Monday after class. So if you come to class tomorrow, if you have questions on the quiz, I'll answer some questions on the quiz for you as well. Get started on the homework. We do have the computer lab here, so even if you don't have questions, you're welcome to come in and work in the computer lab on your homework and ask me questions as you go during class as well.